Welcome back, everybody. Ready to dive into a concept that might seem a bit abstract at first glance? We're talking about projection matrices.
Absolutely. And they're more than just some theoretical idea living in textbooks. They actually have a huge impact on our everyday lives.
Okay, I'm listening. But before we get ahead of ourselves, maybe we can start with a simple question. What exactly is a projection matrix?
Well, imagine you have a 3D object.
Like a cube,
Yeah, perfect. A cube. Now shine a light on it. What do you get?
a shadow, obviously.
Right. And that shadow, that's a 2D representation of your 3D cube. A projection matrix basically does that mathematically. It takes a vector from a higher dimensional space, like our 3D cube, and transforms it into a lower dimensional one, just like the shadow on the wall.
So it's like we're simplifying the information,
Yeah.
but we're doing it in a really specific way.
You got it. And the key is to preserve the essential information even as we simplify. Let's say we have a vector, and it has coordinates x, y, and z. A projection matrix could, for example, eliminate the z coordinate. So what's left?
Well, you'd be projecting that vector onto the xy plane, but the x and y coordinates would still be there.
Exactly. We keep the info that's relevant to that plane.
Okay, I think I'm starting to see the picture. But you mentioned different types of projection matrices, right?
Yeah, think about it. There are different ways to cast a shadow, aren't there? It's the same idea here. We have orthogonal projections and oblique projections.
Okay, now you're just using big words to scare me.
Not at all. It's simpler than it sounds. Imagine you're shining that light directly above the cube, that shadow. It's an orthogonal projection.
So it's like a perfect right-angle shadow.
Precisely. Mathematically, that means the difference between the original vector and its projection is perpendicular to the plane.
Okay, so the shadow is like perfectly aligned with the object. No distortions or weird angles.
You're exactly right, and that's what makes them so useful. That perpendicularity ensures the projected vector is the shortest possible distance from the original to the subspace.
Shortest distance, huh? Why is that so important?
It has big implications in fields like optimization and data analysis. Think about minimizing errors, finding the most efficient solutions, that sort of thing.
Oh, I see. So what about those oblique projections, the ones that aren't straight on?
Well, imagine you tilt that light source. The shadow stretches and distorts, right? It's the same principle. Mathematically, the difference between the original vector and its projection is no longer perpendicular.
So it's more like a skewed or tilted version of the original?
Exactly. And they have their uses too. Things like signal processing or computer graphics where that tilt might be useful. But orthogonal projections, they're definitely the workhorses, the more common and fundamental type.
Okay, so I'm keeping track. Orthogonal is like a straight-on shadow. Oblique, it's like casting the shadow at an angle. But does this actually matter? Like, how does it affect the way we actually use these matrices?
Oh, it absolutely does. The type of projection depends on the problem you're trying to solve. Think about computer graphics. You might use orthogonal projections for technical drawings where accuracy is key. But for something more artistic, where you want to play with perspective, you might use an oblique projection there.
So it's about picking the right tool for the job. Makes sense. I'm starting to see why these things are so powerful.
And believe me, we've only scratched the surface. Projection matrices are amazingly versatile. They give us a way to simplify complex problems while keeping that crucial information. And this has huge implications for all sorts of fields, from 3D graphics to quantum mechanics.
Okay, now you've really got my attention. But hold on, before we go any further, let's make sure we're all on the same page with the math behind this. I think things are about to get even more interesting.
Oh, you're definitely right about that. Once you understand how these matrices are constructed and how they work, you'll really see the beauty and power in them.
All right, let's do it. Hit me with the math.
All right, so are you ready for some math? Now that we understand what projection matrices are and the different types, let's get into how they're actually built.
Hit me with it. But you keep it simple, yeah. Some of us haven't touched linear algebra since college.
No problem at all. We'll start with the most common type, the orthogonal projections. The key here is to use a set of orthonormal basis vectors. They span the subspace you want to project onto.
Whoa. Back up a sec. Orthonormal basis vectors. I think I remember that term, but can you remind me what those are? And why are they important for all this?
Of course. Let's try to visualize it. Picture your typical 3D coordinate system, right? You have your x, y, and z axes.
Right.
Each of those is represented by a vector pointing in a specific direction. Those are your basis vectors. They're like the framework of our coordinate system. Any point in that space, you can express it as a combination of those three basis vectors.
Okay, so the basis vectors are like the building blocks. I'm with you so far. But what about this orthonormal business? What's special about that?
Great question. Okay, so ortho means they're orthogonal to each other. They're at right angles.
Like the corner of a perfect cube.
Exactly. And normal. That means they're unit vectors, so their length is 1.
So we have this perfectly aligned set of building blocks. That's our orthonormal set. Gotcha. But I still don't see how that connects to projection matrices.
It's all about creating a system for mapping the vectors. So to actually build the matrix, you take each of these orthonormal basis vectors, right? And you arrange them as columns in a matrix. Then you multiply that matrix by its transpose.
We transpose, is that like when you flip the matrix over or something?
You got it. You just switch the rows and columns. So simple example, you have a matrix with rows A, B, C, and D, E, F. The transpose would have columns A, D, B, E, and C, F.
Interesting. So we take our matrix, we flip it, and then we multiply, and what do we get?
The orthogonal projection matrix, it's amazing. This process automatically encodes all the important stuff we talked about. The perpendicularity, the shortest distance, it's all baked into that matrix.
Whoa. So it's like we're taking these special building blocks, putting them together in a specific way, and boom, we have a matrix that can project vectors perfectly. What about oblique projections? Are they made the same way?
Oblique projections are a bit trickier. It's not just about the orthonormal basis vectors. There's this extra factor that we bring in, and it kind of skews the projection, tilts it.
So it's like we're adding in a slant. I think I'm getting it.
Yeah.
But can you give me an actual example?
Yeah.
Seeing the numbers always helps me understand.
Absolutely. Remember when we talked about projecting that 3D vector onto the XY plane?
Yeah.
Let's say our vector has coordinates 2, 3, and 4, and we want to project it onto the XY plane. So basically, we get rid of the Z component.
Right.
The projection matrix for that is really simple. It's a 3x3 matrix with 1s along the diagonal for the X and Y components and 0s everywhere else.
So it's like a filter.
Yeah.
It only lets the X and Y coordinates pass through.
Perfect analogy. And when you multiply this matrix by our vector, 2, 3, 4, what do you get? 2, 3, 0. We've projected our 3D vector onto the 2D plane. The X and Y stayed the same, and the Z went to 0.
Wow, cool. So we literally see the math doing the flattening, right?
Yeah.
Taking the higher dimensional vector, bringing it down to a lower dimension, but still keeping the key info.
Exactly. This simple example really shows the power of projection matrices, you know? They can simplify problems without losing crucial information.
Okay, I'm starting to feel good about how this all works. I'm ready to see how it's applied in the real world. You mentioned that projection matrices are kind of behind the scenes, working in lots of different areas, right?
Oh, absolutely. And those applications are incredible, so diverse.
All right, let's get to it. I'm really curious to explore these real-world applications. Let's move on to the last part of our deep dive and really see how projection matrices are shaping the world around us.
I'm excited to share them. Get ready to see how these mathematical ideas, these seemingly abstract things, are actually all around us. They're in the graphics of video games and the algorithms that power machine learning, all sorts of things.
Okay, lay it on me. Where do we see these projection matrices in action?
Well, let's start with something I'm sure you use every day. Computer graphics. Every time you see a 3D image or play a video game, projection matrices are hard at work.
No way, really. I thought it was all about fancy algorithms and rendering and stuff.
And those algorithms rely heavily on, you guessed it, projection matrices. Remember our shadow analogy from earlier?
Yeah.
It's basically the same thing. Projection matrices take those 3D objects, those scenes, and transform them into the 2D images we see on our screens.
So it's like translating the virtual 3D world into something we can actually see in our 2D world.
Exactly. A mathematical translation. And it's not just flattening the image either. Projection matrices handle things like perspective, making things look smaller when they're further away.
Oh, right. So that's how they create that feeling of depth. Makes it all look so realistic.
Exactly. And it's not just about entertainment. Think about machine learning. Projection matrices are crucial for something called dimensionality reduction.
Oh, yeah, we talked about that a bit earlier. But can you remind me how it works?
Of course. Let's say you're a researcher and you're looking at consumer behavior. You've got tons and tons of data on all these customers, hundreds of variables maybe, like their age, their income, what they buy, their browsing habits, all that stuff.
I can imagine. That's a lot of data to try to make sense of.
It's a nightmare. And that's where projection matrices come to the rescue. They can reduce the number of dimensions. But the best part is you keep the most important information.
So you're making the data simpler, but not oversimplifying the problem itself?
Yeah.
How do you decide what's important, though? What to keep and what to get rid of?
That's the really cool part. There are techniques like PCA, principal component analysis. They actually use projection matrices to find the most important patterns and relationships in all that data.
So it's not just throwing data away randomly. It's about being smart about which dimensions are the most meaningful.
Exactly. And projection matrices give us the tools to do that. So you project the data onto a smaller subspace, and suddenly it's easier to see what's going on. You can visualize the data, find those hidden patterns.
Wow, so it's helping us understand these huge data sets. It's creating these amazing virtual worlds. I'm starting to think projection matrices are everywhere. Are there any other cool examples?
Oh, tons. For instance, they're used in robotics. Think about a robot trying to navigate a room and needs to process all this 3D visual data from its cameras.
So it's like giving the robot a way to see depth and distance, like we do with our eyes.
That's it. And projection matrices are key. They help transform that 3D info into something the robot's algorithms can use. That's how it identifies objects, maps its surroundings, plans its movements.
So they're basically giving robots a way to interact with the physical world
Yeah.
using math. It's like a universal translator almost, bridging the gap between these different dimensions.
That's a great way to put it. And we're just getting started. Projection matrices pop up in medical imaging, signal processing, even quantum mechanics.
I think we could talk about this for hours,
Yeah.
and we'd still only scratch the surface.
It really shows the power of math, doesn't it? This seemingly abstract idea, but it has a huge impact on how we understand, how we interact with the world around us.
I know I'm definitely looking at things a little differently now. I never thought about the power of projecting a shadow.
And that's the beauty of it, right?
Yeah.
Math has a way of revealing these connections, showing us these profound insights in the most unexpected places. Projection matrices. Perfect example. One tool. So many possibilities.
Thanks so much for taking us on this mathematical journey. It's been a real eye-opener.
My pleasure. It's all about sparking that curiosity, showing how these seemingly complex concepts can be both beautiful and totally relevant to our lives.
Well, you've definitely done that. I can't wait to see what other amazing topics we'll dive into next. Until then, keep those minds curious, everybody. Remember, the world is full of mathematical wonders just waiting to be discovered.